So quick intro. This talks about, or this coding session is about locks in asynchronous Rust. And they can be tricky because you have your tasks scheduled across multiple worker threads. And if you just take locks in between, you might be blocking your entire worker thread. And especially Tokyo is really sensitive here. So we kind of don't really want to have locks in asynchronous Rust. But then the question is, how do we share state across tasks? You can use channels, but they can get quite messy really quickly. So what I'm going to do today is I'm going to show you a quick toy program that I wrote, and we're going to refactor it from using a lock to not using a lock, but still sharing state across tasks. Okay, time I go. So first, let's show you the program. So it's a little server, and we can run multiple clients against it. And we send messages, nothing happens. If we send the message ping, we get back how many pings have been sent. And this state is shared across the multiple clients, right? So we've got one web server or one server, and we share state across the clients. Easy. Okay, how does this look like? We've got our client here. It's pretty straightforward. We make a TCP connection. We wrap the stream in a frame with a lines codec, means we'll eliminate the items by new lines, and we wrap standard in as well. We make a future select. If the stream gets an item, our protocol between server and client is that we just send the number of pings back as a number. So we'll parse that from the line, and we print out number of pings. And if we get a line from our stream, we'll just, from our standard in, we'll just send it to the server. What does the server look like? Has a TCP listener. We have some shared state, which is the number of pings, and that's the thing that's wrapped behind the rcmutex. Right. And then we have an endless loop, which just accepts new streams and spawns a new task for each stream. We clone the state. We again wrap it in a framed. And then we're going to read each message. If it is a ping, we're going to lock the state. This is where the mutex comes in. We increase the number of pings, and we send it back. So how are we going to change this? Well, we can first start off with what we really want to do is we want to capture our stream in a state machine. So I have a little cheat sheet over here. That state machine looks about looks like this. So pretty much we have one enum variant per state that our stream can be in. We can be in ready to receive, we can be in we're sending a message, we can be flushing the stream, or we can be poisoned. I'll get to the poisoned bit in a bit. Okay, so and then we implement the poll function, which basically will just make progress on our state. We'll take a context, as with asynchronous programming, we'll always take a context. That is where we register the waker and stuff, and we will turn a poll of an IO result with a unit type. We should import poll probably for this to work. Cool. So we can now basically just start with the first part of the state machine. We want to we need to check which state are we actually in. So we're going to match self. But the annoying part here is, or not annoying, or the difficult part is that this is a mutable reference, right? But if you want to have state transitions, we sort of need to get a hold of the current state and actually transition to a new one. So the trick on how you do it is you use memReplace, where you pass in self, and then a socket state, and some kind of dummy state. And memReplace returns you whatever was at the current memory address and gives you back the result. So now we have an owned version of our socket, and we can actually move on to a different state. But first, we need to do something. In ready to receive, we actually just want to receive. So we can say, not self, socket, poll receive unpin, poll, or next unpin, that's what it's called. Right? Question mark that. I'm just going to quickly return poll pending at the end so that all these red lines go away. That's much better. Add a mutable reference. And so we can either read a line, right, which actually is an option. So the stream could have ended. That's when it returns none. So we get a line, or we return pending. Now, if we are pending, we sort of need to, the state is currently set to poison, so we need to set that back to what we currently were at, which is socket state ready to receive, and we pass the socket back in, and we can return poll pending. So a really important part with Rust futures is that whenever you return pending, you've got to make sure that the waker is somewhere registered. We registered the waker in here because we passed the context, and this socket returned pending, so we are allowed to return pending. Now, whenever we get a message, we need to check whether or not it is actually a ping. So we're going to match on the line, which I misspelled here, line, as string. So if it's a ping, don't forget the new line, otherwise it's not going to work. If it's a ping, we want to increase the counter. Well, we don't have a counter here. But what we can do is we can just pass it in. So we say the number of pings. Just take that as a reference, U64. And we're just going to say, well, the number of pings just increased, plus equals 1. Notice how we don't have any blocks here, right? And if it is a ping, we actually want to we need to send a message back. Now, we can't just say socket.send here because we're not within an async function. We can't use await, but we can transition ourselves to a new state that will, once we get there, send a message. So we say self is socket state, send message, and the message we want to send is, I'm going to use the format macro, the number of pings, right? That's our contract. Again, don't forget the new line, otherwise it's not going to work. And the socket. Now, if it's not a ping message, but anything else, this is a bit of a tricky part in our state transition. We need to set ourselves still back to a valid state. At the moment, we're poisoned, so if we read a message that doesn't make any sense to us, which is not ping, we're just going to go back to we are ready to receive again. But now we have an issue, which is we can't return poll pending because our call to poll next actually succeeded. If we return poll pending here, we'll never get called again. Right? So the way you solve these kind of problems is that you wrap the entire poll function in a loop. And you basically try to do as much work as possible within one call to the function. And we can just say continue here. All right? Now this is kind of important. We weren't ready to receive. We polled our socket was ready, we had data in the buffer, but it turned out not to be a ping, so we set ourselves back to ready to receive, and continue again, makes us go to the top, we replace ourselves with poisoned, and we poll again, and if we then return poll pending, we just exit, and we are still adhering to the poll contract. Now, what happens if we actually return poll ready none? That means that our socket has disconnected, so we can just solve this by returning poll ready and an error, and we'll just say this is an IO error kind, broken pipe. That seems good. Cool. Now does this compile? This does compile because we're not doing any of the other state transitions. I'm not going to code these now because that is just always sort of the same pattern. So I'll go to my cheat sheet and we can look at it here. It's like, okay, on send message, well, we'll first poll the socket when it's ready to accept the message. We're going to start send, we go to flush, pending, we stay in our same state. It's always the same pattern. So I'm just going to copy that. And in poisoned, we should never be in poisoned if we do our state transitions correctly. So in poisoned, it's safe to panic, and it's just something that we need to do because of the Rust type system. So this does compile. And, actually, really important part, obviously we don't want an endless loop. But we do have a return from each branch. So kind of an interesting visual check that we can do is, do we have a control flow always paired with this assignment to self? Return self, continue self, return self, continue self. Yeah. So that's sort of like the visual check that we have to make. And this should compile. Cool. Now the question is, how do we actually use this thing? We still need to sort of accept new connections because this just encapsulates one state. And it actually needs the number of pings as an input parameter. So I'm just going to make a thing called a ping counter, which is going to represent the entire application state of that network socket, right? So here we're going to track our number of pings. And we're also going to have a thing called incoming, which is a type from async std that has a lifetime because it's bound to a socket that it's where the messages or the streams are incoming from. And we're going to have some streams. And that's just going to be a list of our socket state. Okay? Now, I've got 6 minutes left. Why am I rushing so much? So, got a function, new, and we're going to, actually, let's not do new. We can just initialize it. Poll. New itself, context again. So when you're writing manual poll state machines is just like poll all the way down, really. And then you just call more poll functions from your poll functions. This is essentially what async await also desugars to under the hood. But you don't get any control over it anymore once you spawn it away, because the only thing you can call on is poll. So you can't really make any decisions on the code that the compiler generates. That's why we sometimes write them ourselves. So again, we loop in here, and one of the first things we do is we say incoming poll next unpin, and this thing, we're going to match on that. If that is ready, which is again, I believe, some string. Yeah, so if this returns ready, we have a new stream. Well, what do we do with a new stream? We just shove it into our vector. Done. If it's pending, we need to actually wrap it in this frame thing so that we are correctly reading lines and not individual bytes on this. Why is this not happy? Yeah, obviously, it should be an entire socket state, ready to receive. Here we go. Now, in pending here, for the moment, I'm not going to do anything. We still need to handle this other case where it's none. We're going to do the same thing, return an poll ready with an error, IO error kind, broken pipe. Okay. Now, we also need to have our streams make progress, right? So what we can do is we're just going to say self.streams, poll for, just go through all our streams with a mutable reference, and we're just going to poll each individual one. So we're going to say streams, which should be singular poll. And now this poll function requires our number of pings variable. And we can just pass that in, right? We've got a mutable reference here, pass on the number of streams, pass on the context. This could fail. And then we match on that again. Now this thing, I believe, it's not what I wanted. Match. So that's a result. Yeah, so that just never happens. Actually, we probably don't want to question mark this because that will abort the entire server if only one stream causes an error. So we're going to say, okay, it's not going to do anything if the stream, this actually should never happen. We could probably statically type check that with the never type, but that seems to never get stabilized, so we don't have it. If it's an error, we're just going to make a print line. Stream failed 2 minutes. Oh, good. Cool. So now what we do if it's pending, well, if it's pending, for now we don't want to do anything, but what we do is at the end of the loop, we say return poll pending. And the reason we do that is if this thing gets all the way to pending, means a waker got registered, we move on to our next thing. If all the streams return poll pending, then we are safe to return poll pending. Now the most important bit here is that actually here, we would also fall to the next thing, but this socket could be making more progress, so we say continue here again. And this should compile. It does compile. Cool. And now we just need to use it, right? So we get rid of all of this stuff that is in our old main. We make a ping counter with number of pings. Incoming is listener dot incoming, empty streams, ping counter. And now all we need to do is call this within a pollFn, which is a helper function. So if you have anything that returns poll and takes a context, you can call it within that and make it into a future. So we poll this, await, unwrap, don't care about that, error, mute, and now we can delete the state. Does it compile? Yes. Does it work? That's a question. Compile the server, client, one ping, 2 pings. It does work. I guess a clap, come on. 50 seconds left. So I'm going to pause here for now. I just want to walk through some interesting things that we can observe here now that we have this architecture. Many of you may think like, this is about 3 times as much code as we had before. How is this any better? Well, it might not necessarily be better. It just has different trade-offs. So one thing we can see is here, we're no longer spawning any tasks. Right? We are handling all streams and everything on a single task, which can be good if you want to sort of limit what kind of system resources incoming clients want to impose on you. If I spawn a task for every incoming connection, even though systems can handle thousands or 10,000s of tasks easily, it's still sort of unbounded growth based on behavior outside of your system, which can sometimes be a bad idea to do. Second, we no longer have any locks. We just track local state in here, and we just pass on the number of pings into the individual stream. Another thing that's interesting here is that it's fairly easy to test this individual state machine, right? It's its own encapsulated thing. It's a module that you can put somewhere, and you just instantiate it whenever you need it. So the code is more modular. And the third thing, and that's sort of what's really exciting and prompted me to share this, is we do a lot of this inside of Rust-Lib P2P. And the reason for that is because it gives us explicit control over latencies and local buffer queues, local buffers. So for example, at the moment, if ping counter is polled, I can see the first piece of work that happens is we're going to accept incoming connections. But that's probably not that good actually, because accepting incoming connections means more work. We should be focusing on finishing the stuff that we have locally to do first. So I'm just going to take this and put it at the bottom. Right? So now I've optimized for latency of finishing all the work that we have on local streams first before I'm taking on new work by accepting more incoming connections. And depending on how complex your network application is, you can make a lot of decisions here, and you can have a lot of influence over have certain local queues be small, dispatch work locally, have your components do work first before you accept new ones.
Hey, sorry, Thomas. Just a word from our sponsor. Just a quick word. Can you sit down on the stage?
Thank you. Hi, everyone. I'm Cal. I work here at Harrison AI. We sponsored the event for today. So thanks a lot for everyone for turning out, being engaged in all the talks today, and all the speakers taking part today. Following on from this event, we're going to be rolling through to Maloney's Hotel. So if you're interested in having a couple of beers or whatever other beverages you might be into, feel free to come along. It's only a 3-minute walk just around the corner. Thank you. Thanks, Thomas.
Thank you. Yeah, any questions to that? Not the beers, this talk, I mean. Really? No questions? What is the next step? You mean with this architecture, or? The next iteration. So what this thing's not handling very well at the moment is stream failures. So what you'd want to do here is you probably want to remove the stream that failed from the list, which is a bit tricky to do because you're borrowing it mutably here, so you have to kind of, there's a trick you can do where you reverse iterate over an iterator and you always call swap, which is an O1 iteration, and you take it out and then you can remove it again. But you will accumulate streams in here that are dead, right? Because we're not removing them here and we kind of really want to remove them. Yeah, that would probably be the one thing I'd add to that. Really, this kind of idea of writing your state machines yourself with poll can just be really interesting if you want explicit control over what should happen in which order, but it's a bit verbose.
So what do you hate most about async?
What do I hate most about async? Actually, how unclear it is whether or not futures are cancellation safe. So cancellation safety in 2 words is, what happens if I drop a future? Will I lose some work somewhere? Like, does the future state hold something that I will never get back or not? And that's actually Hello? Yeah. That's something that's really problematic if you use async and await, because if you select, like in the client here, for example, right, this second argument here, that's always the unfinished future that didn't finish. Right? If I add a variable type here, we see next framed read. In this case, I just know that the future return from framed is cancellation safe, so I can just drop it. But I would have to like carefully read through the library code and be like, is it actually cancellation safe? So that's kind of annoying, and that's, I guess, also an interesting advantage of this pattern is that you don't have to worry about that because you're just polling things, and you will work off each individual item that you get back from that asynchronous component. Cool. Thank you very much.